In this video, we're going to be introduced to complex numbers. Complex numbers allow us to define those numbers which previously, when we arrive at them, we would simply say does not exist. So let's consider the following situation, which is a very common one where we come up with a solution that we would say does not exist, and that's solving a quadratic equation. We've got x squared subtract 4x plus 5 equals 0. We know when we make a quadratic equal to 0, graphically, we're trying to find the x-intercepts. Now, looking at this, I would first say, can I factorize this into a binomial product? But I cannot multiply by two numbers to give positive 5 and add to give negative 4. So I'm going to go straight to using the quadratic formula. So x equals negative b plus or minus b squared, take 4 times a times c, all over 2a. If I simplify this, we've got 4 plus or minus the square root of 16 subtract 20 over 2. And this gives me 4 plus or minus the square root of negative 4 over 2. We would say you cannot square root a negative number, so therefore no solutions exist. This tells me that when I graph this quadratic, it doesn't actually intercept the x-axis. On our Cartesian plane, which represents real numbers. Now we know that the part that I've highlighted here is the discriminant, and it's the discriminant that tells us how many possible solutions we can have to a quadratic. If the value under the square root sign is above 0, we have two real solutions. If it's equal to 0, it's got 1, or if it's below 0, then there's no solutions. But what happens if we can define these solutions, not in terms of real numbers, but in terms of some complex solutions? So we're going to consider the value of negative 1. What happens if we replace the value of negative 1 with I squared? So in turn, this tells us that I would be equivalent to the value of the square root of negative 1. Now all of a sudden we can redefine our solutions, our numbers, in terms of being able to square root a negative. And that allows us to produce complex solutions. So let's consider, before we go back to redefining these solutions, what it looks like to square root a negative number. So if we're trying to square root negative 9, well, this is just the same as the square root of 9 times negative 1, for example. So we could separate that as the square root of 9 times the square root of negative 1. Now we know the square root of 9 is 3, and if we use this definition to say the square root of negative 1 is equal to I, the square root of negative 9 can now be expressed as 3i, a complex number. If we have a look at part B, we've got the square root of negative 196. Well, this is just the square root of 196 times by negative 1. We know the square root of 196 is 14, and the square root of negative 1 we can now define as I, so it's 14i. The square root of negative 20, well, we can define that as the square root of 4 times the square root of negative 5. So it's going to be 2 lots of the square root of negative 5. Now let's redefine this negative 5 as 5 lots of negative 1. So this is going to be 2 root 5 times root negative 1, which is I. So what we've just done here is redefined these values as complex solutions using this complex number, saying that I squared is negative 1, so I is the square root of negative 1. So let's see how this goes if we solve some simple equations. So I'm going to do A for you. So if I've got x squared equals negative 121, this tells me that x is going to be this positive or negative the square root of negative 121. So we know the square root of negative 121 we can now define as the square root of 121 times the square root of -1. The square root of 121 is 11, and the square root of -1 is I. So we've got two solutions here, two complex solutions, positive or negative 11i. So now what I'd like you to do is pause the video and have a go at question 2b, at solving for x, and have a go at question 3. Knowing that we've got I squared equaling -1, evaluate parts A to F. Okay, taking a look at the solution for 2b, let's say that x squared equals -49 on 2. So x will be the positive or negative the square root of -49 over the square root of 2. We know square root of -49 will be 7i on root 2, and we can rationalise this one to say positive or negative 7 root 2 on 2i. In question 3, hopefully you identified I squared as -1. So I cubed is going to be I squared times I, which is just -1 times I, which is -I. I to the power of 4 is like I squared times I squared, so -1 times -1, which is +1. I to the power of 5 is just I to the power of 4 times I, so that will leave us with I. And I to the 6 is just I to the 5 times I, which is I times I, which is -1. Hopefully looking at these, you could see a pattern forming. We could say that in the power of, when I is to the power of 1, it would have a value of I squared is -1, I cubed is I to the 4 is 1, I to the 5 is I, then we've got -1, and this is going to continue. We can see that it repeats every fourth power. So that tells us that I squared is like I to the 20 plus 2. We know I to the 20 is going to be at the fourth power of 4, 5 lots of that fourth power. So that's just going to equal 1 times I squared, which is -1. So complex numbers are real numbers plus the roots of negative real numbers. They're actually given in the form using the letter Z as A plus BI. So they have two parts to them. A real part, which is represented by A, and an imaginary part represented by the value B. We can plot these points on what we call an Argand diagram in the complex plane, as you'll see shortly after. Let's return to our first example, where our solutions were x equals plus or minus, we've gotten the 4 in front there. We've got b plus or minus the square root of -4 over 2. This was our solution to the quadratic we were trying to solve earlier. We realised that our solutions did not exist, but in terms of the complex plane, we have two complex solutions. So if we take each of these solutions, I'm just going to take 4 plus the square root of -4 on 2. Now we can simplify this down to say that we've got 4 plus the square root of 4, which is 2, and the square root of -1 is I over 2. So x is actually 2 plus I, or if we took the negative, x would equal 2 subtract I. So here we've shown our solutions as a complex number. In yellow, I'm going to highlight the value of A in each of these. So A is 2 in each of these. And in blue, I'm going to highlight the value of the B in each of these. In our first solution, B is +1, and in our second solution, B is -1. When we talk about a solution given in A plus BI terms, it can actually be represented on a complex plane. So I'm just going to go to the bottom of our last page and have a look. Here I've drawn what we call the complex plane. Our horizontal axis is represented by real numbers, so that's our A value, and our vertical axis is represented by our imaginary value, the B value. So, for example, 2 plus 3i is represented in the complex plane written as a vector 2, 3, and it's drawn as a vector in comparison to the origin of the axes. So it's very much plotted like a vector. Just like we can see I and j components, we've got real and imaginary components. So our solutions to x squared take 4x plus 5 equaling 0, we had x equaling 2 plus I and x equaling 2 subtract I. So we could actually show those solutions on the complex plane using this Argand diagram. We can do plus I would be our first solution, and 2 subtract I would be our other solution, represented here as plotted like vectors. So now I'd like you to pause the video and have a go at seeing if you can state the real and imaginary parts of the following 4 examples in question 4, and in question 5, solving to find the exact roots of the quadratic equation, and then come back and check your solutions.